Good day. So in this short video, I will discuss the connection between the image charge method in electrodynamics and the Green's function. Okay, so let me actually give you a short outline. So first, I will do some derivations to clarify the role of the Green's function in solving electrostatic problems. And two, then I will connect it with the image charge method. Okay, so that's that's what I'm going to be doing. So the image charge method. Okay, and right at the outset, let me just say a few words. So basically, in electrostatics, we are concerned with, suppose there's some charge distribution, and that charge distribution you can describe by rho of x. X is a function, so x is a vector indicating the position, and rho is the charge density at that particular position. Okay, so that might vary over this object. And suppose that you are interested in, let me call this x prime, and suppose that you are interested in the potential at the particle. So this point here is the vector x, or the position x in your coordinate system, and phi of x is what you are interested in. And in this case, you can write phi of x, and you can take an integral over the volume over rho x prime dx prime divided by x minus x prime. So basically, we have a way of connecting the charge distribution to the potential. Okay, so that's the essential step in solving a wide class of problems. Now, one thing that we know actually is that gradient squared phi of x is equal to minus 4 pi rho of x. That's the Poisson equation. And also we know that gradient squared 1 over x minus x prime is equal to minus 4 pi delta x minus x prime. Okay, so this is standard information, sort of the setup of this discussion. Okay, so that's let me make these 2's clearer. That's the Laplacian, so that's a 2. Okay, so and let me actually say at the outset that in this case, what we call the Green's function is this. Basically, it's the Coulomb potential per unit charge. Okay, so Coulomb potential per unit charge. Okay, so that's where we start. But now we want to actually address different types of problems. Okay, so a different class of problems. Let me actually illustrate the types of problems that we're going to be talking about. Okay, so recall that in the previous year, the charge distribution fixed. Here what we have is some region of space. Okay, so that's a region of space. Okay, but it's a bounded region of space. Okay, so this is important. We're talking about a bounded region of space. And okay, in some cases, at the boundary, the potential is given. Okay, so that's one possibility. The other thing that you might have is so charge distribution, but inside the region. Okay, and another thing that might, or well, instead of the potential in a region of the boundary, it could be that the normal derivative of the potential. So it's the derivative of the potential with respect to the normal. So maybe that might be the normal. And here, that might be given in some parts of the boundary. Okay. And the question is, how do we solve these types of problems? Because how do we solve these types of problems? And this is where the Green's function turns out to be useful. And let me give one of the standard examples to which I will apply the methodology developed here at the end. Is suppose that you have a sphere, okay, and you keep the sphere at some potential. Okay, so let's say you could keep the upper hemisphere of the sphere at V0 potential and the lower at minus V0 potential. And you might ask the question, what is the potential in the space around the sphere? Now notice that this is a little bit different technically from this general example that I gave, because here you are worried about a region which is bounded, but here you have excluded a certain region, which is actually the inside of the sphere. So in this case, it's slightly different, but it's actually the same methodology. Okay, so okay, so basically, this is the types of problems that we will talk about. But let me actually, at the outset, discuss for the mathematical basis of all of this, the divergence theorem. Okay, so that's going to be our starting point. And the divergence theorem says that if you have a vector field A, okay, so you have, and you calculate its divergence, and you integrate this over a region of space. Okay, so this is a volume. Denoting here. So let's say I can draw something to make this indicative. So this is some volume of space. Okay, some volume of space, but it's a bounded volume. Okay, and what the divergence theorem says is that if I calculate the divergence of A over this volume, then I get the same thing as the integral over the boundary of the normal component of A. Okay, so that's the divergence theorem. Okay, so here I denoted by V this volume, and by partial V I denoted the boundary of that same volume. Okay, now what's going to be important is the green identity. Okay, so I don't know if I have enough space here, but I'll start the derivation here. So we're going to consider the green identity. And in order to derive this, what we do is take two scalar functions. So let's say one is phi of x, that's a scalar function, and psi of x, okay? And we form a vector field, A, phi of x, gradient psi of x. Okay, so that's our starting point, and then we apply the divergence theorem to this vector field. Okay, so if we actually go back to the divergence theorem, it's obvious that what we get is that we're going to have an integral over the volume, and that integral is going to be the divergence of all of this, and the divergence of this is the gradient of phi, scalar product gradient of psi, plus phi and Laplacian psi integrated over the volume. Okay, and that's equal to, this is two terms here, that's equal to this integral over the boundary. That's simple. So this part, I'm not going to have space to write it, sorry. Gradient psi, but I will write it on the other page. Sorry, that's dot nda. Okay, let me rewrite it in the other on the other page, so it's actually on the next page, so it actually looks nicer and more readable. Okay, so what we have is the first green, I guess it's called the first green identity. It's volume integral so these two gradients, scalar product plus phi of x Laplacian psi dx is equal to partial v phi of x gradient psi of x dot n dA. Okay, so that's actually the green identity that we are we want. That was our objective, and we could have noticed that if I go back to the original page, I could, in principle, form another vector field by doing the reverse. So I can put psi in place of phi and vice versa. So my vector field would be psi gradient phi. Okay, and if I had done that, I would get another similar identity. So it would be, well, the first term is symmetric. So this would be just gradient phi. Let me actually suppress some of the notation here just to save myself some space. Plus phi, sorry, this would be the psi in that case. Laplacian phi. My psi's and phi's look a little bit similar. Sorry about that. Okay, and this is equal to psi gradient phi, that's phi, dot n dA. Okay, I hope that's readable. But anyway, this is, I want to just, after this is a psi, that's a phi. Okay, and the next step is to subtract one from the other. Okay, and then we get an important identity. I think that's called green identity, so I will just call it that. Green's maybe its second identity. Okay, so the green identity basically says integral phi gradient squared psi, because if we subtract one from the other, the symmetric terms cancel. Okay, so here I suppressed x, that notation, but this is gradient phi dot gradient psi. This is gradient phi dot gradient psi. Okay, and then we have minus psi gradient squared phi, and that's integrated over the volume. This is over the volume that we have chosen, and this is equal to the integral of partial v and phi gradient psi minus psi gradient phi, normal component over the surface of the boundary. Okay, so this is the important identity that we will use. So I'll actually keep it, but I will actually refer to it later. So I will bring it back from time to time. Okay, now what we're going to do is use this identity to derive a relation between the Green's function and the potential. Okay, so first of all, what we're going to do is we're going to take the function phi. I'm going to first of all switch to primed variables. Okay, so I'm going to take the function phi x prime, and I'm going to equate it with the electrostatic potential. Okay, and then I'm also going to take the function psi x prime, and I'm going to equate that with the Green's function in this way. Okay, sorry if you can't differentiate, but this is phi and this is psi. And this is a capital phi that I'm using for the potential. Okay, and now we write this into Green's identity. And we also will use what we know about the potential and what we know about the Green's function. Okay, so next step, Green's identity. So integral over the volume. Okay, and we're going to have here phi x prime. Okay, so let me actually just remind you what Green's identity looks like. I'm substituting, for this one, I'm substituting the potential, but I'm also making everything primed. Okay, so here I put phi, and then I have to put the Laplacian in the prime variable. So maybe I'll indicate that like this, gx x prime. Okay, and I'm going to then have minus g x x prime, and then the Laplacian of the potential. Okay, and that's integrated now over the primed x variable. And this is equal to, and I'm going to change notation here because I prefer this other notation for the rest of this discussion, actually. So let me write phi x prime partial g x x prime partial n prime minus g x prime partial phi x prime partial n prime dA prime. Okay, and now I want to use the information that I have about potentials and Green's functions, namely that the potential satisfies. So I'm going, sorry, all of these Laplacians are on the prime variables. So this satisfies this identity. Okay, so I'm going to substitute that. And a second identity that is satisfied is that the Laplacian of the Green's function has to give us a minus 4 pi times the delta function. Okay, so let me write that second identity here because it doesn't fit up here. So gradient squared g is minus 4 pi delta. Sorry, it doesn't fit here either. So gradient squared g x prime, and that's a prime variable. It doesn't have to be, but that's how we want to use it right now. Okay, so that's another identity. So we're going to substitute all this in here. And we see that, first of all, a delta function would go in place of this. And if I integrate this phi x prime against the delta function, what I get actually is minus 4 pi phi of x. Here I would have 4 pi times the charge density, because here I have the Laplacian of phi. So I will also have then 4 pi integral g x prime rho x prime dx prime. Okay, and this equals that. Okay, let me rewrite this in the way I want to see it. I'm going to take this side. So this is the right-hand side of this equation, which I didn't write. That's what the dot, dot, dot indicates. But I'm going to take this side over on this side, divide by 4 pi, and multiply by minus 1. So I'm going to have actually, with a slight rearrangement, that phi of x is equal to the integral over the volume of g x prime rho x prime dx prime plus 1 over 4 pi, and the boundary term, but with a negative, okay, because we negatived everything, g x prime partial phi x prime partial n prime minus phi x prime partial g x prime partial n prime dA prime. Okay, I'm very glad that this fits the page. Okay, but for now it has been only a mathematical derivation, but let's discuss this a little bit. Okay, so first of all, we see that the potential is given by 3 terms in such a case. The Green's function, which plays the role of the Coulomb potential, so the potential per unit charge, okay, in the particular case, okay, but we'll discuss how to construct it a little bit, at least in one case. And it connects the charge density that's inside the region via the Green's function. It gives that particular contribution to the potential. Okay, so that's the inside contribution. But then there's also 2 boundary terms. And the boundary on the boundary, you either have partial phi partial, the normal derivative of the potential specified, in which case you have this term, or you can specify the potential itself, and then you have this term. Okay, so this is how we can calculate the potential in the case of the types of problems that I've set up in the beginning, when you have an enclosed region via a boundary. And now let us look at some examples. And before I go on, I want to make another intuitive statement. So basically, in the beginning, we set up these types of problems. Okay, so here's the types of problems. Here's that slide or that sheet. So we had a region that was closed off, and we agreed that maybe the potential or the derivative of the potential is specified along the boundary of that region. And now let's think a little bit, because how do we actually fix a potential on the boundary of a region? Well, we have to actually arrange the charges in a particular way outside of the region. Okay, so and the way, this statement itself should sort of ring a bell, that what we're doing here is very similar to what we did, what one does when one uses the method of images to solve a problem. Okay, so that's actually the connection in principle between the Green's function solution of a bounded region and and the method of images. So let's actually have a look at this a little bit via actually the simplest example one can think of, which is, suppose that we have a sphere, okay, and I keep the potential at 0. Okay, I keep the potential on of the sphere at 0, so it could be a conducting sphere, for example, and a grounded conducting sphere, and I put some charge at position x prime, and let's say that the charge here is q, and we're going to take the center of the coordinate system to be the origin. Okay, and what I'm going to be concerned with is the potential at some other point x. Okay, so that's what one thing we know the solution to this problem based on the method of images, because the way you solve this problem is that you put along this ray that I've indicated with the dotted line, you put another charge. Okay, and let me say that this is charge q prime, and let me give it the position y prime. Okay, and then you know that the potential is the charge. So I'm going to cite these results basically, but the potential here is, you can think of it as you can take the potential here to be the sum of the potential from this charge and from the image charge. Okay, so we have q prime divided by x minus y prime. Okay, and we know that from the image solution, so basically you want to fix q prime and y prime in such a way that the potential is 0 on the surface of the sphere, and that's going to be true if q prime. Sorry, I should give I have to give a radius to my sphere. But if q prime is equal to qr over x prime, and we also need to specify this distance y prime, I'm going to specify its magnitude, because its direction is already specified, given that it lies on the ray between the origin and x prime, but r squared over x prime. Okay, so that's actually our potential, which also means that for the outside region, okay, so this determines the potential in the outside region. Keep in mind that in the method of images, you can only put image charges in the region that's not the region for which you're calculating the potential. Okay, so here we have a grounded conducting sphere. Okay, and we put an image charge inside the sphere, but we're calculating the potential for the part outside the sphere. Okay, and and so basically this potential solves that. And what I want to say also is that we can read off the Green's function in this case, okay, because we can just say that the Green's function is going to be, the Green's function is going to be, I can write it like this. Okay, so obviously it's going to be a unit, we put a unit charge at x prime. Okay, so looks like our old friend. Sorry, I missed the minus sign here. This is minus qrx over x prime. Minus, so actually we put unit q. Okay, so even q prime now is going to be unit times r over x prime. So I'm going to have r divided by x prime. This is x vector prime, x prime, x minus y prime. Okay, and the point is that y prime depends on x prime, so y prime determines x prime. So this is actually a function of these two vector variables, x and x prime. So that's actually our Green's function. Okay, so we can solve a lot of problems of different types with that. Okay, so let me actually just make a little bit of an outline of one problem, which is frequently solved like this. And that is a sphere, okay? And I'm going to take hemispheres, and I keep the potential at V0 and minus V0. And suppose that I want to calculate the potential outside of such an object. Okay, now we actually can go back to our potential in terms of the Green's function. Okay, so that's here. Okay, and now we see that we have three terms. So we can look at what types of terms would we have in the actual problem. Well, in our problem, there is no charge density in the region of interest, right? So our region of interest is the outside of this sphere, and there is no charge density in that. So the first term doesn't give a contribution. Then, once we are on the boundary, we know that our Green's function gives 0 on the boundary. Okay, so there's no, so this contribution will not, there will be no contribution from this one either. So all we're going to have is this one. So actually, in this particular case, we can write that the potential is equal to minus 1 over 4 pi integral over the boundary of the region phi x prime partial g x x prime partial n prime dA prime. So that's actually basically this is the key to the solution of this problem. And this is specified because we know that the upper hemisphere is V0 and the lower hemisphere is minus V0. So actually on the boundary, I can write phi as in spherical coordinates. So I fixed the boundary by fixing the radius to be capital R, okay? And I can write V0 as long as theta is in this region, and minus V0 as long as theta is in that region. Okay, so 0 to pi over 2, we have V0, pi over 2 to pi, we actually have minus V0. Okay, so that's actually what we're going to substitute here. The only little bit of a task, and I will do this, this is a very small derivation, but we have to actually obtain this. Okay, so let's do that. We have the Green's function, it's here, okay, but we have to write it in a different form. We have to write it in a form that's convenient. So we have to rewrite it in terms of spherical coordinates. Now, I'm going to outline this solution, and I'm going to outline the solution of a simpler problem, because this actually, even when we take this derivative and so forth, this is actually a pretty hard problem. There's another way to solve this, but that is not so instructive in terms of Green's functions and potentials. The other way would be in terms of Legendre expansion, in terms of Legendre polynomials. Here I would just guide you to the solvable problem of the potential along the z-axis. So that's actually relatively easy to do all the integrals and find the solution, okay? But I won't do that yet. First, I will start evaluating this, okay? So I can write the Green's function, because it's a little bit instructive, all the technical details here, okay? So so the Green's function, but I'm going to write it in a different form. x squared plus x prime squared minus 2x x prime cosine gamma to the power 1/2. Okay, I hope that's reasonably readable. Okay, and the Green's function has a second term, which is minus r divided by x prime, and then here we would have x squared plus y prime squared minus 2xy prime cosine gamma to the 1/2. Okay, let's go back and think about what these variables mean. So here's my point x, that's this one, and here's my point x prime. Okay, and the angle between x prime and x is this one, and that's what I'm calling gamma. Okay, that's what I'm calling gamma here. And here, well, it's this, since y prime lies along the same ray, the angle is the same. Okay, so the next step is to substitute for y prime. Okay, so gx x prime is equal to 1 over x squared plus x prime squared minus 2x x prime cosine gamma to the 1/2 minus r divided by x prime. And here I'm going to have x squared plus r to the 4th divided by x prime squared minus 2x r squared divided by x prime cosine gamma to the 1/2. I hope that's readable. That's a 1/2. Okay, and now actually just to make it, we're going to have to take the derivative. Let's keep in mind what we're doing. We are trying to evaluate this term, and what we're after is this normal derivative. And this normal derivative is basically, it's on the boundary of the sphere, so it's going to be a derivative with respect to x prime. Okay, but then we're going to substitute in place of x prime, we're going to substitute r. Okay, so we can proceed as 1 over x squared plus x prime squared minus 2x x prime cosine gamma to the 1/2 minus r over x prime squared, x squared. I'm bringing the x prime under the square root. Okay, that's what I'm doing. R to the 4th minus 2x x prime r squared cosine gamma, and I ran out of space. Sorry, this is a 1/2. I hope that's reasonably readable. That's an x. So x prime squared, x squared plus r to the 4th minus 2x x prime r squared. This cosine gamma is not readable from my screen. Sorry, this is a cosine gamma. Okay, and now I want to give myself more space too. So let me actually. Okay, so this is the next step. So that's going to be minus 2 x squared plus x prime squared minus 2x x prime cosine gamma to the 3/2 2x prime, and I have also the derivative of this one, which is minus 2x cosine gamma. And I'm not going to have a space problem because I'm going to take this term and do the derivative here. So I have plus r divided by 1/2 x prime squared x squared. I hope I don't have a problem with space because there's a lot of variables there. 2x x prime r squared, it seems, cosine gamma to the 3/2. And here I'm going to have 2x prime x squared minus 2x r squared cosine gamma. Okay, yeah. Okay, so first of all, the 2's cancel here as well as here. Okay, and the next step is, actually we have to massage this term a little bit, okay? Because what we can do with this term is we can, what can we do with it? Actually, well, you know what? Okay, before we go any further, what I want to do is to substitute x prime equals r. Okay, so that's going to be my next step. So let's say partial g x prime partial x prime with x prime equals r. Well, that's going to be equal to, and I don't have space, so I'm going to continue with the second term on the next page, but it's going to be minus r minus x cosine gamma. That's easy. Divided by, well, I suppose I could write here x minus x prime to the third power, because that just makes the notation easier. But then I have to do this one. Okay, so I will do that on the next page. Okay. So I'm going to have here plus r x squared minus x r squared cosine gamma. Okay, and that's divided by r squared x squared plus r to the fourth minus 2x r to the third cosine gamma to the 3/2. And what I'm going to do is, out of this, I'm going to remove, so I will massage this second term. Let's keep in mind that this, so this is the first term, and that's the second term that we are doing here. This second term is actually equal to r x squared minus x r squared cosine gamma divided by r to the third x squared plus r squared minus, sorry, I made the mistake. Well, okay, here we should keep in mind that x prime, so, well, x prime is on the surface. Yeah, okay, well, I will rewrite it, but so anyway, x squared plus r squared minus 2xr cosine gamma to the 3/2. That notation was a little bit clumsy, but I will rethink it. So r squared, okay, and then so what we're left with here is x squared minus xr cosine gamma divided by r. And you know what? I will actually just write here, well, what should, I suppose I could write here also x minus x prime to the third, but keeping in mind that x prime is on the surface of the sphere. Okay, so that's just, that saves me notation. That's the point. Okay, and now the interesting thing is to realize I will. Yeah, I should have I can indicate this here also. That's a little bit clumsy actually, but I just did it to save space. So r minus x cosine gamma, and here I have x squared minus xr cosine gamma. The thing is that when we add these, we see that the cosine gamma terms cancel. Okay, so here I have minus minus, which is plus x cosine gamma divided by this term. And here I have minus, so not plus, of x r cosine gamma divided by r, and also divided by this term. Sorry, that's an absolute value. Okay, so those terms cancel. So in the end, what we have is x squared over r, because this term stays, minus r, because this term stays, this r term stays, and that's divided by, I'm going to write it out fully now, x squared plus r squared minus 2xr cosine gamma to the 3/2. Okay, so that's actually the normal derivative on this of the Green's function on the surface. Okay, so now we have we could actually solve the original problem. Okay, So let's write, so keep in mind, just a reminder of what the original problem is. Here we have the original problem. We figured this out and we already wrote this. So we can write the potential. We can write the potential in the following way. So we have phi x is equal to minus 1 over 4 pi. And it's the integral over the boundary, but the boundary is the sphere. And let me first write, the potential is V0 in the upper hemisphere. Easy enough. And then I write my the expression that I derived. So it's this x squared over r minus r. And I divide by x squared plus r squared minus 2xr cosine gamma to the 3/2. Okay. And now, well, these are the prime variables. We should keep that in mind. And the area element, of course, is r squared sine theta prime d theta prime d phi prime. And we have to just note that we have one integral, the phi integral, which goes from 0 to 2 pi, and the other integral goes from 0 to pi over 2. Okay, and then we have, that's the upper hemisphere. Okay, and now the lower hemisphere is the same with different integration limits. Okay, 0 to 2 pi, and otherwise it's the same. X squared over r minus r divided by x squared plus r squared minus 2xr cosine gamma to the 3/2. And here I also have r squared sine theta prime d theta prime d phi prime. Okay, now I want to actually just, so here is our, here's our sphere again. Okay, and I want to actually just fill in one technical detail. So suppose this point here is the point where we want to find the potential, but this integral is running all over the sphere, okay, the surface of the sphere. Okay, so the points which are, let me call them x prime, which are on the surface of the sphere are, well, these points are, so the x we can write as r sine theta cosine phi, r sine theta sine phi, and r cosine theta, whereas x prime we can write as r sine, well, the same thing with prime variables, r sine theta prime sine phi prime and r cosine theta prime. Okay, and basically I said that cosine gamma is the angle between these two. Okay, it's the angle. So here's the center, and an example of an x prime might be this point. Okay, and that's our gamma. That's our gamma. And this gamma, of course, you can determine from the scalar product. It's nothing more than sine theta prime cosine phi minus phi prime plus cosine theta prime. Okay, and then you would have to put that in place of gamma. Well, actually, that doesn't leave you with an easy integral. Okay, that certainly doesn't leave you with an easy integral. And usually you can, what you can do when you approach the problem from this is do the first, I don't know, 2 or 3 terms, and that's probably still doable. But here's an easy example. So I'm just giving you some hints here for if you want to try. Suppose that you have, you want to actually calculate, so the same situation, V0 minus V0, and you want to calculate the potential on the z-axis, okay? Because in this case, cosine gamma drastically simplifies, because on the z-axis, sine theta is 0 and cosine theta is 1. So in that case, it's just cosine theta prime. And in that case, this becomes easily integrable. So that's actually a problem that's doable by this technique. Okay, thank you for your attention, and goodbye.